Okay, so let's go ahead and get started. We have a lot of material to cover today. So my name is Abhishek Gopal. I work 80% in the Department of Oceanography and 20% at the Texas TAMU High Performance Research Computing. And for today's short course, we'll be talking about how to use some of the more recent Python-based utilities to post-process many types of climate model output, but specifically catered to the community Earth system model. And before I go forward, does anybody have any issues hearing or seeing me? If so, you can use the chat feature to let us know. So you can use the chat, let me know if I'm not audible, or you can't see me, or you can't see what I'm sharing, and so on. So with that, I just want to leave this slide. So if you're completely new to Ada, you can use some of these resources to just get a sense of what to do. And so even if you're new to Ada, I think with the commands I've listed, you probably don't need to do anything more, but this is for, if you want to explore on your own time, so these will be good resources. And if you have any questions, of course, you can fire up in the chat window, but more generally, always submit tickets to help@hprc.tamu.edu. And some of the other relevant short courses you might be interested in, and these are like specifically Python and scientific Python and using Jupyter Notebook, which we'll be using a little bit of at the end. So if you're interested, go to hprc.tamu.edu/training/index.html. Okay, so the structure of today's course, I'm assuming many of you are have a geosciences background. And even if you aren't a geosciences person and you're more looking for processing large amounts of data, I think this course will still be helpful, and I'll come to that in a bit. But first we'll start by talking about the community Earth system model, how it outputs files, where it outputs files, and then we'll talk about the CESM post-processing package, which is developed by NCAR, the National Center for Atmospheric Research. And then we'll get some hands-on examples on how to generate these. So you have these, the raw model output and what sort of post-processing goes on in there and how to generate diagnostic plots. And then once that is wrapped up, we'll start moving to the more recent advances in Python for geosciences. And I'll be showing you a few examples which use the Jupyter Notebook. And we'll also have a short break in the middle. Okay, so the target audience, like I mentioned, you're a geosciences researcher who either you run your own CESM model, good for you, or you don't run your model, but there's plenty of publicly available CESM model datasets available on the internet. Or you might be using your group's in-house database. So either way, so if you're doing one or the above, you might either already be using these parallel tools to enable your post-processing workflow, or you might be using NCO, NCL, CDO, MATLAB, or Ferret for doing your post-processing. And they are very powerful tools. I still use them from time to time, and there's nothing wrong with using them. So in this course, I'll just present some alternative ways of restructuring your workflow that could make your work faster. And of course, this doesn't just apply to the CESM model. You could, in theory, apply many of this to MIT GCM or any of the other sort of climate models you run, or WAR for ROMs, those sort of things. And before I go any further, I want to give you a little bit of my background, my educational background. So I have a PhD in mechanical engineering, focusing on computational simulations of fluid mechanics, specifically reacting flows. So I come to this with a more of a fundamental fluids background, and now I'm in the oceanography department. And the way I look at it, many of these tools, maybe the first set of tools I'm going to talk about, maybe they're overly like designed just for like CESM and like geosciences folks. But the xarray and dask examples I'm going to show you at the very end, they can be applied to any big data set problems. So I wouldn't say it's just a course for geoscience folks. And the reason I sort of mentioned my background also is, since I come in not with an oceanographic background, I may not be able to answer specific questions about, how do I compute this, the mixed layer depth quantity, in equatorial Pacific region or something. So maybe I don't have that scientific background, but I can help you more with the computational aspects of it. And there's always chance to talk more later about this. Okay, so I think I've already covered some of the expectations. So the first thing is just to give you sort of a general background about some available Python tools to process CESM data. And you'll learn about some diagnostic plot sets. The hope is also, you're able to run some of your own cases and get some results and take a look at them. And also the stuff I'm going to show you at the very end, it's just a peek at some of the very exciting technologies that are coming out. Okay, so yeah, so let me go ahead and talk about let me first check my chats if anybody wants anything. Okay, got it. Okay, and actually before, I'll also show you my browser. So hope everybody can see my browser as well. So this, I'm sure you have received the course webpage. And so it's got slides from this fall, and also this text file, which is pretty much all the commands you'll need to be issuing on Ada. And of course, this class would involve a login to Ada, and how to log in is presented in the text file. So you want to download this text file and keep it for reference. Okay, so the community Earth system model. So it's one of the many. So I'm not going to be talking too much about this model itself because you probably know much better than me. But it's an open source model developed by the National Center for Atmospheric Research, and these are some of the. So you have a top level driver called the coupler, and for doing different types of physics, you have these different types of components, which can be either active, meaning they're being computed on the fly, or they can be data, meaning they're being pulled from a database. So it's a pretty huge code. It's like 1 million plus lines of code. And you could have like many sessions just on CESM. So obviously the focus of this course is more, either you have access to, you run your own CESM code, or you have access to CESM datasets. So how do you access some CESM datasets? There's several ways. So the NCAR website, which is listed, the first one, that lists some CESM 1.3, CESM 1 experiments, some CESM 2 experiments, and I think you have to create an account on the website, and you can download those data sets from there. And also you have what is called the Earth Systems Grid Federation, which compiles a list of many of these climate simulations. So if you're going to be, if your climate model output is going to be used by the IPCC, it has to conform to several specifications. And so there are a lot of these model data sets that are available on Earth Systems Grid. It's pretty vast. Many groups in the world publish their data sets, and there's like plenty of data. So what I've prepared for today is, so because I'm part of the IHESP laboratory in the Department of Oceanography, we have our own high resolution data sets. And I've compiled a very, so we're not going to use high resolution because of like memory requirements, but I'm going to show you on some low resolution examples on some low resolution data sets. But you can find all these data sets in Scratch Training, CESM Post data sets. So let me actually show you what I'm talking about. So for a lot of this course, I'm going to be using the TAMU HPRC portal. So if you're not already on it, all you want to do is just connect to the VPN, the TAMU VPN, and go to portal.hprc.tamu.edu. And you're presented at the page like this. Click on ADA On Demand Portal, and you'll get something like this after logging in and doing a two-factor authentication. And then I'm clicking on clusters and doing ADA shell access. And that opens up a page like this. There's another, you have to enter your password, two-factor authentication. And this is my ADA console. Let me check if there are any questions. Okay. Okay. So I'm going to be going to Scratch Training. Sorry, Zoom is sort of. Scratch Training, CESM Post. So this is going to be the directory for this short course. So over here, I hope everybody, this font size is readable to everybody. And if not, please say something in chat and I can try to change that. Okay, so one of the questions is there any advantage of going through the portal versus like a regular command line? And for this purpose, not really. So so that's a good question. So if you're comfortable with like other ways of going to the command line, just use that. This is just an equivalent way. So you can just do SSH username at ada.tamu.edu. And you enter your password. So it's the same thing. Okay, so this is our directory. And over here, I have this data sets. And I also have downloaded this, the text file containing all the commands, which you can use with your favorite text editor. So yeah, so this should be pretty, I think, pretty explanatory. And of course, you don't have to look at everything. I'll walk you through which ones to use. But in the data sets, basically, I have two data sets for you. One is, so I'll come to this later, but these are coupled simulations involving the atmosphere, ocean, ice, land, and river model. So it's a pretty comprehensive model, but this is like the low resolution version of the model. And let me just show you how one of the files look. And of course, if you've used a CESM model output before, you know it's in Ocean HIST, and we'll come to that in a bit. So a lot of these are just files of .nc. And this long name before this, that's the name of the case. And this is like the year and month. And okay, so that's enough for now. Okay, so I've described where the data sets are on disk as an example. And more importantly, you don't need to copy them to your local directory. Just let them be wherever they are. For your examples, we're going to automatically pull them from the location. So there's no need to copy it to your directory. So typically in a in a CESM model run, so if you're running your own CESM case, you first need to download the source, the CESM source code into a directory. And then you create what is called a case. And from that point, you build the case and you get another directory. And there's another directory called an input data directory that contains all the boundary conditions and all the forcing files and those sort of things. And so all this is to say, these are directories that exist in the CESM framework, but the one that we really want to focus on is the short-term archive. So all CESM output is written to what is called this short-term archive directory. So this is an example on one of the NCAR servers, but we have, it'll vary for your case. But the most important thing is it depends on this variable called dout_s_root. And this will be important when it comes time to like configuring some of the post-processing cases that you want to run. Okay. So under the short-term archive directory, you see how each component has its own folder, and under each component, you have a folder called hist. And you also have logs, but the location of logs can vary depending on what sort of CESM run you have. So mostly you just want to pay attention to this hist. And this hist is short for history files. And so when CESM writes its model output, it's writing all the quantities such as temperature, salinity, let's take the ocean case. It's writing fields like temperature, salinity, sea surface temperature, velocity, and all those, the density, for example, at a particular instant in time. So as the model evolves in time, it's just writing the fields either as daily output or like monthly averaged output, but as a single instant in time, instead of it being a time series. So the native CESM model output is a history file format. And that's the files I showed you when I went into the location. But for certain applications, you may want to transpose it to like a time series format. And what is a time series format? Some people also call it like just a variable. So if, for example, you want the entire SST, the sea surface temperature, as a function of time and all in a single file, that's the equivalent of like a time series file. I know these are like terminologies. It might differ from how you use it. But the history file, it's like all the variables at one particular time, or maybe a few particular time steps in a single file. And whereas the time series, you only have one variable, SST, let's say, at all particular times. So why I'm making this distinction is the data sets that we're going to be using, they have the history file format. But when you download data sets publicly from the internet, they're usually going to be a time series format, because it's like, I think if you have experience, you'll know it's more convenient to work with than history files. And I guess there's also a question, how do you convert history files to time series files? And I think we'll get to that in a little bit. Okay, so before we go any further, I think I showed you let me go back. Okay, so this is the case we're using. And this part just means it's a component. And this page from the NCAR website like explains like what the exact notation is, because when I first started using it, I had no idea what it meant. In this case, the letter B alone means it's a couple model run. So for example, B stands for a coupled case. This is correct. Okay, so a coupled case meaning the ocean component is active and the atmospheric component is active, apart from many other components being active. But you also have many other component sets where just the atmosphere is active along with land. Or you could also have like just an ocean and ice run, like this G here. And then the next one, it tells you about the version information we're using. So here we're using, this E refers to CESM. So we're using E13, so that's CESM version 1.3. And then we have a short name for the component set. So over here, it has a B1950 C5. So what it means is, so this is a couple model run starting from the year 1950. And so we're using historic conditions starting 1950, and it's also a control run. And specifically for this experiment we ran, the control run means no CO2 forcing. And that's as much science I can tell you about that. And there's also a case where we have, sorry. So we also have another case where it's TR. So TR is the transient equivalent of it. So the reason why you have a transient run and a control run is the transient run has a like the historical CO2 forcing until a certain year. So we run from 1950 to 2050, and it's got the transient run has got a historical CO2 forcing, whereas the control run doesn't have any forcing. And this is important. Why I'm mentioning this is we'll come to it later in a little bit. Okay, so maybe I don't want to overkill with information here, so I'll move on to the next slide, but you can take a look if you have any more questions. Okay, so the next thing is all these files are what is called an HCDF format. So I'll go a little hands-on here. Assuming everybody can see this, so I'm going to use this utility called netcdf dump. And so what it does for me is, so basically it did netcdf nc dump print header, and I'm just printing all the quantities in this. And most likely, if you're in the geosciences field, you already know about this. So this is the typical structure of an HCDF file. You have these, you have what are called data variables. You have dimensions. So it's pretty suitable to a geoscience model output sort of a thing. So like, since we know we're going to be using a lot of netcdf files, and sorry. Okay. So I'm sure a lot of people in this class have already used one of these many packages. NCO, NCL, and the last one, PyNGL and PyNIO. So those are Python packages, so I want to leave them aside for a little bit. But NCO and NCL were developed by NCAR, and like some of the most popular tools for post-processing netcdf files that exist. The CDO is also a tool similar to NCO, but I don't think it has like as much features as NCO. And some people also use MATLAB and IDL to write scripts to post-process their netcdf files. And some of the things I want to mention about all these packages is many of them are run serial, and some of them do have some rudimentary like parallelization, some threading sort of a thing. But when it comes to running on like multiple nodes, like you typically have on supercomputing clusters, these are not tools which scale up. So, or another way of saying would be it's actually pretty powerful and like full featured for a small set of like netcdf files, like a small file. But when you start moving to higher resolution data sets, they're not fast enough, and they take up a lot of memory, which may not work for all our use cases. So the alternative I'm going to talk about, and before I go to that, let me just mention the post-processing workflow. So I already mentioned how the native model output is a history file format. And then depending on your, depending on what exactly you want to do, the type of computation you want to do, you may decide to keep it as a history file or like convert to a time series. But you, and then one of the other things you may want to do is, for example, the atmospheric grid. It's on a fairly irregularly spaced grids, and so you may want to convert it to a more regular grid. So you may want to do a regridding process, which involves interpolation. Excuse me. And so steps 1 and 2, they're sort of optional, and 2 is sort of semi-optional, because if you don't have scripts which work with the generalized coordinate system, then you're computing the derivatives is going to be a challenge. So that's why you want to convert a native grid to a regular grid. So step 3 and 4 are what we're mostly going to be focusing on in the first half of this course, and maybe even like the whole course. So those are computing time averages, climatology files, meaning how a quantity varies across many years, like what's the trend like every month in like, let's say, 100-year duration. And then you also have zonal averages. And after step 3 is done, then you generate diagnostic plots. And lastly, if you want to publish your data sets to something of a more a standard format, then you have to deal with step 5, which I don't, if you have questions, you can ask me later, but we're not going to go through that. Okay, so the CESM post-processing tool that we'll be talking about, and I'm going to tell you how to obtain it in a little bit. So basically, it conforms to the workflow I mentioned previously. So if you look at, so you have these model time slices or history files. So we have this tool called PyAverager, and it's packaged within the CESM post-processing tool. So PyAverager works on history files and generates more history files, but these are averaged files. And then the diagnostic scripts, which are in NCL, act on them and generate these diagnostic plots. Similarly, like if you want to do step 1, which is convert history to time series, we also have a tool for that. And we also have a tool for converting the time series files to a more standardized output format. And one of the nice things about the CESM post-processing tool is, let's say you don't want to use these diagnostic scripts because maybe you don't like how the plots look, or something like, oh, maybe it doesn't plot everything that you want. You still have the flexibility to just use the PyAverager step and generate the time averages and climatology, and then plot them yourself. Like if you use a MATLAB script to plot them, use a MATLAB script. Or you have a serial Python script, you can use them. So that's up to you. So all these steps, they can be used, like you can use them like a proper workflow from 1 to 5, or you can use them, you can use whichever component you like. So you have this flexibility. So one of the first steps in obtaining the CESM diagnostic tool is go to the GitHub page and clone it. So a little bit of a background. So the CSM post-processing tool was originally developed by the folks at NCAR, NCAR CGD. But much of their workflow and the installation procedures were tailored to NCAR machines. So even if you try to like install it on your own machine, it had a little bit of a conflict. But the project I work for, the IHES project, so we work with folks at NCAR. We work closely with folks at NCAR who thankfully ported many of these packages for us from the NCAR, NCAR specific, so configuration. And so much of the work can be credited to Alper at NCAR. And so based on Alper's work, I did a little more modifying to simplify the installation process further. So this is not required for the purposes of this, this short course, because I'll be telling you how exactly to source the package. But let's say you want to try it out on your own some other time. You could click on this link. You could clone the package. You can follow the installation process. Okay. I think I'm just about on time. Okay. So the first step. So at this point, I would encourage yes. So you really don't want to. So the steps I have previously. So do not try this with your Ada account, because for one, it installs a lot of packages which can quickly run through your quota, your file quota. So the best case scenario, like the standard usage scenario that we have both at NCAR machines and on Ada with my group members is we have a single installation managed by, so on Ada it's managed by me, and everyone who wants to use it will follow some procedures to just source that material. So how do we do that? Okay. So if you have your Ada command line ready, you can go ahead and do all these. So the first step is, I always advise doing a module purge, because you never know what conflicting modules you have. So best to clear that out of the way. And so the mini conda package is mostly only necessary for using this source activate command, but largely we're using this Python package. So make sure you have both of these packages loaded, and then you want to follow these commands. So let me do that myself. I think I already have those modules. Okay. And if you go to my text file, you'll see all those commands there. And so once I do this, you'll see how the command line changes. So just the beginning of the command line changes to this path. So what this means is we have switched to this. So what is actually happening is this path here. So scratch training, CSM post processing. So CSM post processing is the name of the package that we downloaded it. But when we ran /create Python environment, what it's what it's doing is it's created a Python virtual environment called CESM-N2. And I think this would be an appropriate time to talk about virtual environments. So there are, so if you used Python, so for many years, I used Python without any sort of virtual environments. So what I would do is I would download, so if I'm using Linux, I'd have an easy way of installing Python. And if I wanted any packages on top of it, let's say NumPy or something, I just use pip install NumPy. And what would happen is those packages would get installed. Let me check the chat. Okay, so for these first set of commands, it doesn't matter where you do them at this point, but after this, you do want to navigate to your Scratch directory, and I'll give you instructions for that in about a bit. So continuing on with the Python stuff. So if I wanted any package like, let's say NumPy, it had already come pre-installed in some cases, in some rare cases, but the other way would be I would install them manually with pip install. Pip is like the installer for these Python packages. But we quickly run into a problem also, because a lot of the times we have many different packages, and sometimes they conflict with each other, and they don't always play well with each other. It's not a problem if you want like 5 or 6 packages, but when you start using more and more of Python, you have many packages and maybe even different versions of each package. And so there's also this other way, which I started learning, maybe a couple of years ago, and that is to create what is called a virtual environment. And if you're aware of like virtual machines in the context of like running, let's say, a Linux within a Windows, it's kind of it's not the same. Technically, a lot of things are different, but it's similar in spirit. So you can have this sandbox-like feature and just put in just the packages you want. And then anytime you want to work with those packages, you just activate that environment and then run all the Python scripts. So this also allows for your system Python to be different from this Python stuff here. So this is a good way to avoid conflicts and keep very specific packages, in like sort of a sandbox. So when you're doing source activate, that's what we're doing. And when you see this in front of your command line here, basically it's meaning that's the sandbox you're using. And to confirm it a little bit more, I do which Python, which is supposed to give me the path for where this Python is being obtained from. And you see how it's being obtained from this environment here. So those are some basic checks to make sure, okay, we're on the right track. So the next step is first to cd into your Scratch directory. So cd Scratch, that takes you to your Scratch directory. And I have a lot of junk in here, but so you next want to do create _ post process. So I think I want to stop here and first, so after you do source activate this line, does everybody get this environment correctly? So that's step number 1. So if anybody has any, questions about this, or it's not working, now is the time to let me know. Okay, so I'm going to create a case called test. Okay, maybe there's already one called test. So I'll just create test. And so it's using some executables in my Python virtual environment, and once you run this command, you should get all these messages and it should say success. So let me know if it's not working, and we can try to work with you and get that to work. So, and once that those things have been generated, you'll see a lot of these files have been generated. And it can be overwhelming at the start, but let's take it one by one. So you'll see some XML files like env_diags atmosphere.xml. And you'll also see these files which don't have any sort of extension, but they're actually job submission files. So if I open them, I'll see these are, so if you used the LSF job submission system before, and maybe you're more familiar with Slurm, but LSF is an equivalent job submission system to Slurm. So what this is doing is it's just requesting an appropriate amount of memory and processors, and then hold on just a second, and activating the required modules and activating the proper environments, loading the required modules, and finally in this step it basically instructs to start the averaging process. Okay, so you don't need to know all these details right at the start. So I'll slowly walk you through what are the files that are important. So steps 1 and 2. So if you've not tried it at this point, please try it and let us know if you have any issues like working with them. So this is the most important thing to go on forward. So. Okay, so going forward, the CESM post-processing tool, it's not entirely in Python. So this, I printed this out from the GitHub page for the CESM post-processing tool, and you can see most of it is actually written in NCL. And Python is like 16%, like even less than HTML. So why is that? And so let me take you back to this slide over here. So you'll see how it's divided into all these different components. So some of the components are like they do the heavy hitting computational work, including PyAverager. It's like the data intensive part of the CESM post-processing tool. Similarly for PyReshaper and PyConfirmer also requires like a lot of, it's also a data intensive task. And so these are written in Python with MPI parallelization in the most case, and we'll come to that in a bit. And the rest, so this is like a very simplified schematic. So if you actually took a look at the source directory, you may not be able to make a one-to-one mapping of what I'm saying here versus what I'm saying here versus what you see there. But this is like the logical schematic, if you will. And let me check my chat very quickly. Okay, so if you get the error with the loading shared libraries, then you especially want to make sure the Python 2.7.15 FOSS 2018B, that's present. So if that's not present, you will definitely get the missing Python shared. So that is the reason I'm trying to load the Python shared, Python module before activating the source and the creating process. Okay, so going back to this a little bit, I mentioned how the heavy hitting tasks are written in Python with MPI parallelization, whereas it still uses NCL for a lot of other tasks, and primarily plotting, regridding, and those sort of things. And the reason for that is there is still, there have been a lot of developments in Python for geosciences. but it's going to be a couple of years before, at least a couple of years before like Python can catch up with NCL, because NCL, like there's been a team of developers at NCAR like working on it for a lot of time, like a decade or more. So a lot of that plotting functionality, very specific to, you know, specific grids and so on, is available only through NCL for now on. So, and NCL still forms like the base of this package. But like I again said, like you have the option of not using NCL and just using some of the Python-based utilities too. Okay, so any other questions? Okay, so this is what I wanted to cover previously, and now I'm going to talk about why use this. I want to try to convince you that it's a good tool to use. So on your left side, you're looking at how, so PyReshaper converts the history files into time series files. And there are several ways of doing this. So if you look at an NCO script, it typically works serially. So it first, let's say, looks at slice 1, and it serially converts the data here. So this is field 1, meaning, let's say it's SST. And this could be SSH, the sea surface height. So a serial program would be limited in like data bandwidth, and you know, it's like to basically transpose this from history to time series, working serially versus this is an equivalent parallel thing. So over here on the left, everything is running on a single core, and obviously it's going to take a lot of time, and it requires a lot of memory. With this sort of approach, a parallelized sort of approach on the right, we see how it can now run on 4 processors, and each of the 4 processors can begin like simultaneously writing fields to. So, for example, they all work simultaneously on field 1 from slice 1, then field 1 from slice 2, field 1 from slice 3, and so all these tasks are distributed parallelly. And why is this a good thing? You can see in terms of like the performance. So over here, so for example, the POP is the ocean model. And if you're looking at a 1-degree grid, which is normally considered a low resolution grid, you see how, so this is the time taken. So you want lesser time taken. So NCO versus PyReshaper, the red versus the other colors. So you see, there's not that much, it's still a difference, not that much of a difference, but the difference is like drastic when it comes to like a high resolution 0.1 degree ocean grid. It's pretty drastic. And like this is like the selling point. So, so not everybody may use PyReshaper all the time or need to use it. So let's also talk about PyAverager. So the averaging process with PyAverager versus NCO works similarly. So it's parallelized with MPI and uses multiple cores at the same time as opposed to just a single core, right? And if you look at some low resolution slices on the left, you see there's like still, so you're looking at duration. So again, lesser is better. And so Swift, I don't want to talk about because I haven't used it before. But NCO and PyAverager I have, and you see there is substantial savings. And the savings get better for a high resolution file. A POP 1 degree, a LAN model 0.25 degree, and so on. So it's like a 15 times performance improvement. So that's pretty drastic, I would say. Okay, so parallel tools are good, and if you're using a serial tool, it's not. There's also like more rudimentary ways of like parallelizing them. For example, on the TAMU ADA cluster, you can use something called TAMU Launcher to launch many of these tasks in parallel too. And depending on the case, it could actually be a good thing sometimes. But also, it implicitly assumes you're working on different files. So which is not always the case, because if you're working on many of the examples I'm going to show you in this case, you're going to be working on the same set of files. So that sort of parallelism is not going to be very ideal. Okay, so we talked about what sort of tools that are there for reshaping a file, transposing a file, and averaging a file. And next, I also talked about how NCL scripts are used to generate these diagnostic plots. And now I want to talk a little bit about what sort of diagnostic plots these are. Okay. So AMWG in this case means the Atmospheric Modeling Working Group associated with CESM. And so they have their own diagnostics package. And I want to go back a little bit to this slide here. So this entire diagnostic part of this package is just a combination of products from different working groups. So OMWG is like Ocean Modeling Working Group, PMWG, Polar Modeling Working Group, Land Modeling Working Group. So this is the diagnostic page respective to the atmospheric model. And I'm going to show you more of that in a bit. But generally speaking, there are like three main categories of these diagnostic plots. You can first do model versus observation. Of course, this requires that you feed it a certain type of like observational data in the background. And then you can do model versus control. So for model versus observation, it was computational experiments versus observational data. Then model versus control is two different runs. And here is where I was talking about the transient run and the control run. So for example, if you wanted to compare what happened to the sea surface temperature with a historical CO2 forcing compared to a case with no such forcing, or sort of an artificial sort of a control run, you could do that in a case like this. And meanwhile, these set of plots, the model time series, they're just quantity versus time series sort of thing. I think I want to stop at this point and ask if there are any questions in whatever I've covered so far. And so you can raise your hand in the chat feature, in the participant feature, and we can unmute you if you want to ask any questions. So, okay, so continuing on with how these plot sets look. So for the ocean diagnostics plot, and I'm going to give you an example from over here. Let me see where it takes you. Okay, so this is an example that's publicly available on the internet. And so this is actually an older version of the diagnostics page that we'll be looking at. And let me go back to my presentation. So some of the basic sort of plot types you'll see are like horizontal, like contour plots for like quantities, you just want to visualize at a particular depth level or something like that. And you can they also have like velocity vector fields and 3D fields like zonally averaged, and also like horizontal mean versus time and depth. So this is the x-axis is increasing in time. You have depth, but it's also averaged in the horizontal direction. So both latitude and longitude. And we'll also see some examples from the cases I have previously generated. Actually, it might be a good time to look at that now. Actually, let me go back and show you that. So one of the nice things about the portal is I can also look at files just from here. So one of you previously asked me what's the advantage of using the portal. Sometimes I want to use the command line and it generates a PNG file, and I like to be able to like just go and look at it like directly, and I find this to be convenient. So going to our course directory, if you go to this directory called post-processing cases, and I'm going to this folder called low resolution control, and this folder called proc. And so these are some diagnostics I've generated previously. So I can just click on view, and this is going to be the header page. So if I click on this link, it's not going to take me to the appropriate link. I need to go to that manually. So let me click on this. Okay, so these are diagnostics for the data sets I've provided, and I'm going to ask you to generate in a few minutes. So for example, looking at the curl, and you have all these different, so you have like temperature and salinity at different depth levels, velocity components at depth levels, you have temperature, TNS, anomaly versus depth. So different types of plots. And you might have a question about how do I add new sort of plot quantities to this? And I'll talk about that in a little bit. Okay, so back to our presentation. So we have these type of ocean diagnostics, and for atmosphere, you have vertical contour plots. Okay, here's a question. Hold on. Yeah, so Yi has a question. Yeah, go on.
Yeah, so sorry. I can ask question after that you answer this question. So, I mean, it's not related with this question. I have a question, a general question. So, could you finish that and then I will ask.
Okay, sounds good. So yeah, I'll also give you time at the end of the class to like ask me more general questions. So yeah, if you have anything particular, like please bring it up now. Okay, so with the atmospheric diagnostics, similarly we have vertical contour plots like quantity versus pressure, and also like it varies in terms of latitude and longitude. And also we have horizontal contour plots. We have vertical profile, so it's averaged in the horizontal direction. And you have annual cycle plots and Taylor diagram, which I don't fully understand the scientific basis for, but I believe it has to do something about measuring the uncertainty of models. And so if you want to look at a sample page, it's over here. And also we're going to generate our own diagnostics. So, and similarly for ice diagnostics, we have some contour plots, some time series plots, and we also have land diagnostics. So in terms of the diagnostics that I can really help you with, because I have some experience, those are atmosphere and land, sorry, ocean and atmosphere, and to some extent ice. But land is not something I have really run a lot, but I can, if you have any more general questions, feel free to bring it up at the very end and I can see how I can help you. Okay, so here's what we're going to be doing. So typically the workflow, like once you've created a post-processing case, it involves going to env post-process to edit some files. Edit some quantities in there, and also env diags ocean and diags atmosphere, and I'll come to that in a bit. And then you edit the job submission script, and you first submit the job to compute the climatology, time averages, and so on. And then finally, you submit the job to generate the diagnostic plots. And to go over this a little, to clarify this a little more, so similar to how there's ocean averages, if you go into your case directory that you created, you'll also find something called ATM averages, ice averages, land averages, and so on. So in our example, we're mostly going to be computing ocean averages, but I think if you want to try atmosphere averages, I think it should work too. And I can help you with it if it doesn't work. So, okay, so that said, now let me go through. So first, let me open up this variable. I have a hard time with the Zoom upper panel. Sorry about that. Okay, got it. Okay, so I'm going to go back to Scratch training, CSM post. And here is where, so the folder you want to look at is pp_cases. So I have a couple of folders here, but you want to look at LR_control. So the plots I showed you previously, they're generated from this directory. So there are two files you mostly want to look at. So the first and most important file is env_postprocess.xml. Okay. So we're going to open that up, and you can use your favorite text editor to take a look at it. And so basically it's an XML file. And what is going on is, so you have, so basically, so the ID represents the variable and the value represents what's the value for that variable. Okay. And let me go back to my presentation. Okay. So there are many such variables here. So the first one is the location of the case root. And the next one is something called post-processing case path. So both of these are going to, so in this case, both of these are going to point to the location of the folder you're in presently. And for us, it was pp scratch training CESM post, pp cases / LR control. And then the case is the CESM case name, and the dout s root. If you remember from the time I showed you the CSM model output structure, this is the location of the short-term archive. And so this env post process is looking for that folder because that's where it can find the history files. And okay, and some of the other variables would be, if you go down, so over here you see the dout s_root. I've set it to one of my data sets. So that's my scratch training CSM post data sets, then the name of this case, right? And the next step is the scripts want to know what sort of grids you use. Okay. Okay. I will pull my short note. Okay. Thanks for bringing that up. Okay. So once you, the post-processing tool wants to know what grids you're using. So here's a grid called, so the atmospheric grid here is NE30. And how do I know that's the name of the grid? Because that's also in the case name. So there's an advantage to using this sort of a big case name. You have all the information there. And so this represents the atmosphere grid. And then, wait, hold on, just a second. Yeah. And then you also have G16. So G16 is short for GX1v6. And I'll come to both of these in just a second. But over here, we're just configuring the atmosphere grid, the ice grid, the land grid, and the ocean grid, right? And now, of course, you'll have the question, what are the grids talking about? So these grids are more complex than anything I've used in grad school, where, because I'm from a fundamental fluid mechanics background, we're mostly using Cartesian or like curvilinear grids, or even like finite, like unstructured grids, but these are a different level of them. So if you want more details, I've given you the appropriate links to help you, but there is some meaning behind all these code words, and typically you wouldn't understand them until you sort of followed through to the documentation and took a look at them. But also the understanding is that if you're using these data sets, you already do have some understanding of the model grid. Or if you don't, it's good to have that information before you do anything further. Because if you don't have a regular grid, all the derivatives you're going to compute are going to be incorrect if you're going to incorrectly assume it's a regular grid. So it's for these reasons that all these grid information, they're like really important. Okay, so now let me go back to this. So these are some of the values I had to set, and let me go down a little bit. So we're not going to be changing anything at all here. Okay. And this I've already showed you. And similarly now, I'm going to go. So first I showed you env_postprocess.xml. So that's universal and that's common to all the components: atmosphere, ocean, land, ice, everything. But now we're going to go specifically to ocean diagnostics file. And so that's this file. So some of the important quantities there are, first is called the ocean diag observation route. So this is, I've copied some of the basic observational data sets we have so that we can make these plots. And going down, you will also have many directories that you need to tailor if you're deviating from defaults. And so some of such quantities are, for example, previously I talked about how you can generate three types of diagnostics. One is modulus is observation, modulus is control, modulus is time series. So you can, set these to true, false, as you like. And also, it wants to know about the format of your netcdf file. So you want to give it that. And finally, you also have to mention starting what year and ending which year are you going to average, or you want the tool to average. So that's this quantity over here. Okay, so with all this mentioned, I want you to try out a case on your own. So you're going to do, first of all, create a new post-processing case. And how you do that is, let me pull up the text file. Okay, so you're going to say create post-process case, -case, and the name of your case directory. So once you do this, you will have generated a file. And then you can either do two things. So you can either run the case as it is. So without doing any sort of changes, you can just do, let me go back a little bit. So you just create a new case and you don't have to make any sort of these changes. Just generate, so just issue these commands: bsub ocean averages, and then check in on the status of your job. And when it's done, you're gonna bsub ocean diagnostics. So that's the first exercise. But if you also want a little bit of a challenge, here's a challenge. So you're going to create a post-processing case, and you're also going to edit the postprocess.xml and ocean diags, env diags ocean.xml. I configured them so that they ran for a control case perfectly without any changes. But all you're going to have to do is make changes to them so that they can do a model versus control case. So of course you have to give it the proper information for the control case. And then you're going to submit ocean averages and you're going to see how that's going. Yeah, so I want you guys to try this and let me know if you have any questions. And I'll be giving you hints from time to time. So. And of course, please raise your hand if you have any questions. And so when you create your default case, what you'll be seeing is you'll get a folder that is very similar to this LR control. So everything that you're going to get in your post-processing case directory is going to almost exactly match these files. So in this case, all you have to do is just submit ocean averages. So B sub less than ocean averages. And then after it finishes, you're going to check on, or you're going to submit ocean diagnostics. And for the more adventurous folks, the other task is to make sure the control, so let me go back to the control case. So when ocean averages finishes, it's going to output all the files to this directory. So it'll be under proc for post-processing, ocean, and at first you'll have this file called Climo. And over here, if your job is generated successfully, you'd have all these different files coming up. Okay, and so for the people who want to try the transient case, you can take a shortcut. You don't even need to run your control case. So you can directly point your case directories to use the ones from here. And how do you do that? I have a solution here. So if you take a look at, so this is my directory. So scratch training, CESM post, PP cases, low resolution transient. So over here, if you take a look at env diags ocean and modify your files to suit this, you're gonna know how to do that. Any questions up till this point? Okay, so let's take a short break here and we will meet. So the time now is 2:46. We will meet at 3:01. Okay, so hope you had a nice break. Let's get started again. So if, for those of you who managed to run ocean averages, you will have some of these files, some or all of these files. So the first set are the climatology files. So it's like the quantities are averaged for each month. So let's say you have year 1950 to 1960. It's month January averaged for all the years. Of course, a lot of people already know that. And then you have just yearly average files for each year. Then you just have a simple time average across all time records. And you have a M average file, which is just a concatenation of just the climatology files. And I want to show you what it's exactly talking about. So I'm going to go to the control case. And like I mentioned, so under the case directory, you want to go to proc. And under proc, it goes to ocean. And if you run the other components, you'll also get an atmosphere and ice. But after the post-processing step, what you'll have is just the CLIMO directory. So at this point, you'll not have a diag for diagnostics. So just going to the CLIMO, you will see a lot of files, more than what I listed there. But pay attention to, so these first set of files, they're just yearly averages for each of the years. And the T average file, as I mentioned, is just the time average, complete time average. And then you have these files, which are just the climatology files for each month, right? And then an M average, which is just a simple concatenation of all of these. And in addition, I'd also requested specifically that the tool, the PyAverager, do basin averages. So this is like GLOW is short for global, Southern Ocean, Pacific, Indian, Atlantic, Labrador, etc. And there are like many regions like this. And because I'd requested some basin specific plots, it's also done that averaging. And the nice thing that you'll see at this point is, even if you decide not to use much of the diagnostics package, you still have a tool that generates these climatology files faster than most serial tools you'd use. I would say, faster than serial tools you'd use. So even if you don't want to use the overall diagnostic packages, and there might be some reasons for that, it's still a good idea to consider using just this averaging part, because it can be very fast. And it's especially fast. I mean, this is just like, we just average for like year 35 to 45. And I think in your example, you'd be averaging for even a fewer number of files. But typically you want to average for 200 years or 100 years or something like that. So it's going to be pretty expensive if you try to do it on a serial, with a serial program. So that's this alone is like the advantage, because most of you already know how to deal with netcdf files. So here you have these netcdf files, so you can plot them, do your analysis scripts from this point onwards, and it's still good. So it's like a combination of plots. So okay, so those are the plots. And then the next exercise, if you want to try it, you already have the scripts ready. You would typically make the changes in env_diags_ocean. Check the ocean diagnostics job submission script for correctness. And what do I mean by that? Go back. So this is a job submission script like anything else you'd have seen, like if you'd used Ada before. So you can just make changes to all the defaults here. So the number of cores, the amount of memory, and of course, I requested a very small amount of memory because I want us all to be able to try it out at the same time. But if you're running a job for like a large averaging case, you'd need sufficiently more memory and like cores. And typically I'd say, I typically would run it on like 1 or 2 nodes. So like 20 or 40 cores and like with the corresponding amount of memory. And the time, usually it's like 10, 20 hours or something, because those are like big jobs we're running, especially for the high resolution files. So all those changes would be made here. But of course, for the purposes of this exercise, you don't have to make any changes. All you need to do is B sub ocean diagnostics, right? And you're done. And then it's going to be generated for you. So, and I want to show you, I think I already showed you a little bit what it looks like. Let me go back. Okay, so we took a look at these diagnostics. And just to recap on where they're located on disk, so you saw under prop ocean, we had a climatology folder, and that contained all the generated climatology files. And similarly, after we run ocean diagnostics, we'd have a diagnostics sort of directory. And this would contain, so a lot of the image files are PNG files, but what stitches together is HTML. So you'd have an index.html, and because we requested model as observation and model time series, all the plots are under there. So if you go under that, you'll have, it contains all these plots. And be careful about downloading them because it also sometimes copies these netcdf files, so they can be extremely large. So don't do that. Just download the PNG files. And so that is exactly the folder I'm displaying here. And so we looked at, so for example, I look at salt. So this is just the global zonal average of salinity for this case. Similarly, you have like basin specific depth profiles and all those sort of things. And also like for folks who know MOC, it also computes the overturning circulation stuff. And similarly, of course, we have the atmospheric plots. Let me also show you. So, so similarly, these are, if you run the scripts for the atmosphere averages and atmosphere diagnostics, you'll get climatology files and like monthly climatology, seasonal climatology, zonal average, and so on. And then going to the diagnostics thing, this is the index.html you want to view. And for example, I could go to a contour plot, plot relative humidity in the winter time. And yeah, there you have it. So this first panel is just the case. And these are observations from ERA 40, and then the difference. And of course, you'll have so the one thing I haven't covered, because it's sort of outside the scope of like what I'm able to like show you, is how to obtain these observational data sets. But the understanding is, as a geoscience researcher, you already have some knowledge of that, or or if you talk to me later, I can maybe think more about how you can access them and those sort of things. But the understanding is typically you have access to these observational data sets, and all you have to do is place them under a directory, the observational data root, and then make the necessary changes in the configuration files to be able to use these in these plots. And with that, yeah, so this is an exercise for you to try. I'd strongly suggest trying this out, or at least checking out what the directory structures look like. So to repeat myself, so you want to go to this directory, the PPE cases, and then look at the LR control and transient cases. Those are the most recent ones. And you want to go into the proc directory and take a look at what sort of files it's generating. And of course, that's an alternative to you generating your own files and investigating it for yourself. Okay, so I'm a little bit behind time, so I'm gonna speed up a little bit. So that is like general overview of the post-processing tool. So these Python-specific, these Python-based MPI parallelized tools offer like significant performance improvements over NCO, MATLAB, and even like parallel MATLAB and so on. And it's even better for the high resolution model output. And if with CMIP 6 coming, a lot of the data sets are like increasingly higher and higher resolution. And the primary purpose of these diagnostic plots is not for your everyday research purposes, because if you're doing research, you need you're looking at a specific quantity that may not be covered by the existing diagnostic plot sets. And the question is how easy or hard it is to add that. And I'll mention that in the next slide. But instead of modifying the diagnostic plot sets, you can use the generated climatology or like the time averaged, zonal averaged NetCDF files and do your own analysis from that point, which brings us also to some limitations. So as I showed you, like it's a combination of many different packages from many different groups, and in terms of like documentation, it's not always the greatest, and that's an understatement. So if you know exactly what you're doing, you may be able to like add new diagnostic sets, new plots to that to the workflow, and everything will be great. But for most people, I would suggest using the first part, like generating the ocean averages or the atmosphere averages, ice averages, land averages. That's the more straightforward part, because the second part, for some folks, maybe the ocean and atmospheric folks, it's more straightforward if they already have those plots that they want in those things. But the suggested use case for those plots is not for doing, like specific research. It's more, is my model on the right track? Is it, is this model dependable? Is there anything globally wrong in any of the, things? And that's more earth sciences question that I can't really answer. So I defer to you. And some of the other things is there are a lot of data sets which are like moving to the cloud of late, especially with the publicly available data sets. And there are these newer tools that can actually work with them directly from the cloud. But this diagnostic tool typically assumes you copy everything to wherever you're working in, and that's the extent of that. So you move the data to wherever your computations are. But some of the newer tools can actually move the computations, to the cloud, to wherever the data are. So there are like different paradigms which are like coming up that can open new doors. So if there aren't any other questions about the CESM post-processing tool, or if you have more general questions, you can feel free to ask me at the very end, because I want to now switch to something else. Okay, so let me go forward with that. So the first step for you is to go to portal.hprc.tamu.edu. And so this is going to be a more interactive session than what we saw before. And I hopefully that was a little interactive too, but I think this is going to be a little more interactive than that. And I'm going to show you what exactly you do. Okay, so you go to portal.hprc.tamu.edu, click on ADA. And of course, you need to be on VPN to have access to this. And you're going to click on interactive apps, and then you're going to go to Jupyter Lab. And these are the specifics you want. You want Anaconda 3-5.001. Likely that's the only package listed. And for your path, you're going to use this as your Jupyter Lab environment to be activated. And just like I mentioned the concept of Python virtual environments for the CESM post-processing tool, this path is another Python virtual environment I created just for the purposes of the short course. And of course, if you're wondering, the packages in this virtual environment and the one we had previously, they're not the same. They might have some overlap, but they're very different packages. You want to request 3 hours, 4 cores, memory per core, 1 GB, and click on launch. And yeah, it's going to take a little bit of time, and you can let it be. Meanwhile, if you have access to a command line, of course, this is assuming you already have done the first step. First cd into your scratch directory. And then you want to either do git clone. So git is already installed on Ada. So you have you use git clone and the name of this link. Let me quickly. Yes, the course slides are there, and there's also a text file containing these instructions. So if you go to, sorry. So if you go to the text file, I've also given you the links over here. Okay, and if you don't want to use Git, the other thing you can do, I have this folder over here, which is essentially the same thing as what's on GitHub. So you can just copy that directory using cp-r, that directory, and to your scratch. So assume already cd to your scratch directory. Okay, so those are some preliminaries, and let's look at what do you want to talk about now. So Pangeo is basically sort of ever-growing, like a unit, like a galaxy of Python packages tailored for geosciences. And so these things, so you see like different levels of them. So the base level is everything runs on Python. And then Jupyter is what we're using as an interactive interface into Python. And so as you go up, it's more higher level stuff, and this is more lower level stuff going downwards. And so xarray and dask are some of the more important packages we'll be discussing today with respect to Pangeo. And xgcm is also like, so Pangeo generally refers to all of these packages, but you may only be using like portions of them, and like, but still they're in the same sort of like universe. You can like pretty much use them interchangeably. And all this is up and coming. So many of these packages, they're like, they have, I would say, they've been in development for like a couple of years. But if you consider how long NCL and NCO and those sort of packages have been in development, so these are definitely like, it'll take a couple of more years to like mature and reach the same level of like potential as NCL or NCO. But what they lack in terms of like maturity, in terms of like the breadth of what it can do, it more than makes up for it in like how trivial it makes like parallelization and those sort of things. So specifically, when you talk about Pangeo, like one of the popular use cases is you could be running what is called a Jupyter notebook. You could be running like a Python script on your own laptop, and that interfaces via a web browser to compute nodes running on a HPRC cluster like Ada, or it could be even on the cloud. And then these two packages, xarray and dask, that's where a lot of the magic happens, and like it works, like it scales many of these tasks in such a way that they work from everything from a laptop to to a really powerful cluster. And of course, I'm not giving you much details here, but let's walk through what we're talking about. Okay, so maybe I'll also start looking at the notebooks. Okay, if you looked at this tab, you want to click on, if it said running, you want to click on connect, or it could say queued sometimes. Hopefully that's not the case because we requested a very small number of resources. So I clicked on connect, and now I'll be taken to the Jupyter Lab environment. So I have a lot of these open files, which I'm going to try to close them. Okay, so let me backtrack and first talk to you about xarray. So xarray is the most fundamental package in what I'll be talking to you about. So xarray is a Python package. And what it's really good at is reading an etcdf file and understanding what is coordinate data, what is dimensional data, what are attributes, and what are data variables, and how, for example, if there's a field called temperature, that's a function of time and latitude and longitude in the netcdf file. xarray is going to be able to read that file and very simply understand how that file structure looks. So on the left side on the right side so I'm going to walk you through this in the notebook. But just as a preliminary example, you see like how with a very simple command, I do xarray.open dataset of a netcdf file, and instantly it understands a lot about what netcdf file it's looking at. So firstly, it's like a very convenient in-memory representation of a netcdf file format. And it allows, so at deep down, it's using a lot of technologies. So the reason why this map is important is, so if you pay attention, so xarray is actually built on what is called NumPy. And NumPy has been around longer than xarray. And it's like a fundamental like array processing package with respect to Python. And NumPy is pretty powerful, pretty vast. There are a lot of functions and everything it provides. So xarray is still based on that. So that is a good thing because it is not it's not re-engineering new things. It's still making use of what exists at a fundamental level, but building on top of it. So that is some of the advantages of this new programming paradigm. Like, we don't simply write new code just because we want something different. We still make sure it's we can use whatever we can use of the existing frameworks. Okay, so before I go any further, let me. Okay, so I'm going to my Pangeo binders, you can actually go to your scratch space. So this is why I wanted you to go to your scratch space. So if you click on this button here, you can go to your scratch space, and then I selected Pangeo binders, and I'm going to click on the first example here. Okay. Any questions up till this point? Like any issues that came up or anything about what I talked about? Okay, so I'll keep going. Okay, so first of all, like some of you may not have used a Jupyter notebook before. So I briefly want to like say what it's doing. So a Jupyter notebook is just an interface to Python, right? It's more an interactive visual interface to Python. So what I'm writing here, and this box in blue is called a cell, and right now it's not been run, but I'm going to run it, and everything inside is just a Python code. And when I say import xarray, it's importing the Python package xarray that exists in our Python virtual environment. And similarly, matplotlib is another package we want, cartopy is another package we want. And I can run this cell by just clicking this arrow here, okay? And then it's gonna turn to the star here, and it's like grade. And so it's actually running in the background. And then once it finishes, it's gonna come up. So basically what I'm trying to do in this first example is just open the xarray package, import the xarray package and some other packages, and open a file. That shouldn't normally take this long, but okay. While that is going on, I'm going to talk about some other packages in the Pangeo universe. So we talked about xarray and how it understands a netcd format file. But xarray doesn't understand grids, or specifically like we have these staggered grids with some variables on one of the grids and the rest of the variables on a staggered grid, like for example in a C grid. Xarray doesn't understand that. So for example, if you want to take a derivative, Xarray is not good at derivatives, at least not with this sense of understanding. So there's this package called xgcm that is built on top of Xarray. So Xarray is already built on top of NumPy, xarray, xgcm. You see how it's reusing code. So that's like a good thing about Python. And that's a good thing about, that's like a software engineering best practices you want to try to keep usually. What's working, you want to use it instead of try to reinvent the wheel. So xgcm does a lot of stuff, including like implementing spatial derivative operators. So that makes life much easier for you. And so xgcm was developed by folks who work a lot with MIT GCM. So, and the consequence of this is it directly understands C grids, but if you want to make it understand pop grid, which is I think it's an A or a P grid or something, it doesn't directly. So there's like some workarounds to make it understand that. And then I'll come to matplotlib and cartopy. So matplotlib is just a plotting library in Python. It doesn't have anything to do with geosciences. It's a very general plotting library. It can plot lots of different things. Now, cartopy is, it does a lot of things, but a part of what it does is also it interfaces with matplotlib to plot map projections, either like static map projections, like what you're seeing on top, or like even like pulling like satellite data, like MODIS, like bands and everything dynamically from the internet to, plot it for you. So these are like pretty, like the 4 or 5 packages I described so far, they're pretty powerful. Okay, so it took a little longer than expected, but we have imported our package. Okay. Any questions so far? I cannot find my scratch in Jupyter. Okay. So you also can do, okay, so there are a couple of questions. The first question is, how do you how do you open that path? And so typically, so Georgie has this question about how to find the scratch space in Jupyter. And so, so the scratch space is the default space with which the Jupyter lab launch from the ADA portal starts up with. So if it doesn't, maybe you want to try to relaunch it. But so you want to click on this button, the file browser. Okay, you don't have the folder thingy. Okay. Okay, so you can also do another thing. If you only have the home directory, maybe download the notebooks. So clone it to your home directory and access it from there. So it doesn't necessarily have to be a scratch. So whatever you have access to, like, please download it to that. So if you don't have access to your scratch. And the other question is, there's no module named xarray. And so that's a good question. And so it's important that when you load, so you click on Jupyter Lab and make sure you're loading this module, because this is the Python virtual environment with which we start our Jupyter Lab. And I believe that should do it. If it's not working, it'll be probably better to, like, if it's still not working after specifying this setting, we could probably take it to at the end of the class. So maybe you could follow along now, Colleen, and we could try to resolve it at the end of the class. Okay. So I'm going to go ahead with these notebooks now. So hopefully you're able to get to this point. And if not, maybe if you wait half an hour, we can get it resolved then. So in the first step, we just loaded these couple of modules. In the next step, what I'm doing is I'm trying to open an netcdf file. So I just say file name is scratch training CESM post, and then it's the full name of the netcdf file. And this is a file you should have access to. And then I just say xr.openDataset of file name, and that gives me a dataset object, DS for dataset. And I'm going to run this, and it's going to come up with an object of type xarray.dataset, and it's going to have all these dimensions. I'm going to quickly look at the questions. Okay. So you see how it has all the dimensions from the, so you can also double check this with the netcdf dump, nc dump. And you see all the coordinates that are here. There are two types of grids. Of course, at this point, xarray doesn't know what, how t-long and t-lat are different from u-long and u-lat. So it just treats them as two different arrays, right? And so there are a lot of these variables over here. And I'm going to go to, let's say, SST. And just clicking on that, you see the dimension of that. It's got a time dimension, an nlat, and an nlon, and it's a float 32, and it's just a simple NumPy array. So it's a simple NumPy array at this point. So it's sort of a dressed up way of, like, a more presenting a more basic information. So that's what it is at this point. So far, so good. Not that impressive. It understands what those things are. But now you can do nice things such as printing the dimensions. You can just say ds.dims, and it'll print out all the dimensions. ds.chords to print all the chords. It can also access, so the dot operator basically is an accessor. So you can either say ds.salt, or you can even say ds dot this way. So they both return equivalent answers. And now salinity is a 4-dimensional variable. So now you have an extra dimension z_t here. And you see for each of these variables, it comes packed with the corresponding dimension. But of course, you also understand here how it's bringing along both u long u lat and t long t lat. But obviously, it doesn't understand that it doesn't need both. So at this point, you can also say stuff like ds.salt .icell, and you can slice along a dimension. So we saw how salinity was, it had like these 4 different dimensions, and now we sliced it across 1 dimension and leaving 3 dimensions. So now comes the cooler part. So just the same way, you can just say ds.salt.icell and see how these operations are just like being chained, like one after the other. We can chain one more operation. We can say ds.variable name .select .plot, and that quickly plots a quantity for me. Of course, if you notice, it's plotting versus nlon and nlat, which are just sequentially increasing numbers. And so it's not a, it's not correct. It's not a, it's a very quick plot, but it doesn't use any projections. So now comes cartopy, like I mentioned before. So because xarray doesn't by default understand projections, it depends on this other library called cartopy. And cartopy, so in this, I know there's a lot of code here, so let's walk through it little by little. So the first line, it just creates it's fig equal to plt.fig, and maybe you don't need to know all the details at this point, but what it creates is this canvas, this big canvas, this 14 times 16. And then in the next step, we specify that these axes are not just like some normal linear sort of axes, but it uses this projection. We can make, so the first line is based on the library matplotlib. And the second line is also matplotlib, but now the library cartopy is involved. And the cartopy library is the one with the projections. So we say the projection is cartopy.crs.plate_carry. So that's the name of the projection we're using. Okay, once you've said that, basically there's like space in memory for like that sort of an object. And now we go and say, instead of saying, just using like sequential numbers for longitude and latitude, we're going to more specifically use the t-grid, the longitude and latitude from the t-grid. So we assign these variables, and then we plot temperature. Because temperature is a 4D field and we're plotting a horizontal contour, we want to slice it appropriately. So we say ds.temp.icell. And then we use this function ax.pcolorMesh with just these 3 variables, and then the transformation you want to use again. Okay, so when you run that, you're going to get a map like this. So this is just a map, a contour plot of the temperature, and at the first vertical level, and time t equal to 0. Okay, so like you'd see, like compared to a typical Python workflow, like how you read an etcdf file, or how you read a data file, and like how you plot it. This is a much faster way. And of course, here there are a bit more steps involved, but you see how like xarray allows itself to like plot very quickly, and over here it interfaces with matplotlib to like plot very seamlessly. So those are like some of the advantages you're seeing of like how xarray can be different. And now we're going to see more features of CartoPy. So in this example, how we have like all the land in white. Over here, what I did is it's the same plot. I've just turned on grid lines, and I'm plotting the coastlines. And the coastline data is, so all of these data CartoPy downloads from the internet. And to avoid, because we're running these on Ada compute nodes, which don't have access to the internet, if you look all the way on top, what I did was I pre-downloaded everything to this directory here, datasets/CartoPy features, and that's where all these map files and those sort of things reside. So CartoPy doesn't look for it on the internet, but normally it would. So over here, we've pre-downloaded that information, and I'm making it plot land. We can even like plot stuff with elevation over land, and I'm also plotting lake just because. And then finally, like saving that figure is just a single command. That's sort of similar to MATLAB probably. And yeah, so it's also fairly straightforward to zoom in on a region and so on. Furthermore, instead of contour plots, you can also do much more simple like line plots. So over here, I'm just manually specifying. Okay, so we saw how the first dimension was time. The second dimension was z_t. So I'm just plotting all, so for a fixed point in horizontal space and time, I'm just plotting all the vertical profile of salinity. And maybe it should be the other way around, but this is just to show you how simply you can make a plot. Okay, so any questions? Any questions up until this point? And you can raise your hand if you want. Okay, so moving on. So some of the calculations are also very simple. So I can do it. So if I want to average across time and depth, I can simply say ds.temp.mean. And then I can just specify the dimensions in the form of a list. And what comes out is just an average. So this is how simple it is to average the temperature field, like with a single command. And these are like designed to be so simple because this is like designed to be interactive. So there's a lot of like behind the scenes processing going on to make sure a command as simple as this can give you the results that you want. So, and you see how it's averaged, and these are the average quantities. And the not a number is because of the land dimension you're seeing. Okay, so I want to see if, okay, so at this point, I've talked a little bit about xarray and what it basically is. I haven't talked about XGCM, and probably that'll be the subject of a different course, but know that it sits on top of xarray, and it provides access to many of the spatial derivatives. We just don't have a lot of time to get into that in this short course. And we've used matplotlib and CartoPy. We do not use XGCM, but I'm able to answer questions later if you want. So this we already did. So now we move on to the little more complicated thing, which is dask. So, so you can think of, so the Python tools the parallel Python tools that we used previously in our the first part of the course for the CESM post-processing, that all used MPI parallelization. dask, meanwhile, is different from MPI. And how it's different is, with MPI, you have to explicitly structure your code to be parallel. There is no other way around it. So if you have a serial code, and if you want to make a parallel version of it, you're going to have to start from scratch. That's basically how it is. But with dask, of course, like, maybe it's not a fair comparison. If you have a serial Python code, you still have to rewrite it. But it can be far more simple to enable some basic parallelization, because it does a lot of implicit parallelization, like, very quickly. So basically what dask does is it has these collections, or you can also think of them as data structures. So xarray, that's like a data structure. And it takes these data structures and it looks at them, and let's say you want to compute an average, like how you computed the mean of a data set. It takes a look at what sort of operations you're requesting and constructs what is called a task graph. And I'll show you what I mean by that in just a minute. And then it runs them, like, parallelly on as many cores as you have. That's basically what dask does. So now let's look at the second notebook, if you have it, or you can also take a look at it later. Okay, so here's some text if you want to read later. So in this case, we talked about how to open a file using xarray. Over here, what we're going to do, it looks very similar. We're doing almost the same thing. The only difference is there's no chunks here, and there's a thing called chunks here. And if we run this, hope I have everything. Okay, so if we run this, it still looks very similar, but unlike here, where it's all NumPy arrays, here it's suddenly dask array. So just specifying what is called chunks made xarray use dask. So that's as simple as that. So it's already using dask now. So now if we print the temperature field, it's going to be, so in the previous case, if we printed a temperature field, it was a simple NumPy array. Over here, what has happened is, instead of being a simple NumPy array of like size 2 GB or something, it's now split it up into many chunks, 36 chunks of size 60 MB each. So it's like a big problem, a big temperature variable has been decomposed into smaller and smaller chunks, or like small chunks, 36 small chunks of size 400 by 600. And that is what we requested. We requested chunks of size in lat 400 and lon 600, right? So that's what we got. And these are not, even though fundamentally each chunk is a NumPy array, still now dask is in control. And I'll come to that in a bit. So another key difference between what has happened here and what has happened in this example is when you requested to open a data set, it opened the entire file. But here, when you did an open data set, it actually has not loaded that into memory. So whatever it's showing you, it's just giving you an idea of how the file looks like, but it doesn't know the actual quantities yet. So that is what is called lazy loading. So dask doesn't load anything into memory until at the last minute when it really needs something. You can read more of these later over here, but let me give you an example. So I have ds.temp here. So now I'm going to compute the average. So I'm going to say ds.temp.mean. Okay. When I run this, it'll finish like very quickly in a matter of like milliseconds. And what is actually happening is dask hasn't computed it. And you might find that very weird. So what is it doing? So dask only computes it when you really need it a certain way. So we can also force dask to make that computation by saying ds.compute, or I could have said ds.temp.mean.compute. So running this, it takes about 17 seconds. So this is when we actually have the computation. So you see the difference between over here and over here. So the compute function forces dask to make like an execution. But before you do that, it hasn't made anything. And the reason why dask is so shy of like computing anything is because maybe it's possible that you don't want the mean, the mean of the full field. Maybe you just want the mean of, even though you said ds.temp.mean, maybe you actually wanted just the mean of one vertical slice or some horizontal slice. And maybe you're going to say that later. So whenever you say that later, dask is going to have that information. So instead of jumping at the chance to compute the whole field at the get-go, dask waits until the last minute to if you change your mind, or if you want to need like a portion of the data set, dask is going to compute that at the very end. For example, if you try to plot it, dask is going to compute. Or you can also force it by saying this compute. So that is what is lazy loading. And another thing that is going on that you have no idea about is this compute operation is also inherently parallel. Okay, and so to explain a little more about that, so first I'm gonna redo a couple of things. So previously we opened like a file that had like 36 chunks for every temperature field. So we're gonna rechunk it a little bit just so that there's 4 chunks so that it's a little easier to understand. So each chunk is 500 MB, okay? And totaling that times 4, so 2 GB. So that's how the temperature field is chunked now. Now, what we're gonna do is dask has an inbuilt function called visualize. So we're just going to do ds.temp.mean and call the visualize function on that. And what this will generate is the task graph that I was talking about, the task graph in this middle step here. So this is what it's generated for us. And so it's a big picture. So we want to start at the bottom. So this rectangle here represents data and the circle represents function. So it's circle function acting on data, because that's what programs do, right? Functions act on data. So the first part is open data set acts on this data here. So we saw how there were 4 chunks in this case, and you see how there are 4 chunks here, 4 chunks in the spatial nlat nlon. So it's still the same order of dimensions. So it's opened 4 different chunks. And for each chunk, and remember, like we call the mean, right? So it's going to try to combine everything. Like so because these are 4 different chunks, dask now has the option of loading them separately, calculating the mean for each thing separately, and then like combining them together. So that is what is happening here. So it has 4 different open data set functions. There's mean chunk here. It only computes the sum or the number of elements. And here is where the actual aggregate happens. And once the aggregate happens, it just returns a single value, right? So you see how that mean operation as like dask, you didn't have to do anything. It simply did this in the background. And the nice thing about this is this can run parallel on 4 cores. So each of this strand of this graph can be allocated on a core. And they'll all be running parallelly on those cores until they reach this point. So at that point, everything has to be collected to one core, and then you have the output. So you see how like you didn't have to worry about parallelization at all. All you need to do was like specify the chunking. dask did everything for you, and it wouldn't even load data that's not strictly required. So there's a lot of magic going on behind the background to make this happen. So and there's a lot of details here which unfortunately I probably won't cover because of time, but I think it's explained enough so that you can go through it. And I mentioned chunking, and it is also important, like how you want to chunk information. Like here I just specified some sort of like chunking, but there are like specific rules on how to declare these chunk sizes and so on. So I'd suggest you go through it, and like there's a lot of examples on the internet, and you can play around with that. And one of the cool things about dask is you can also like, if you're so interested, it also comes with this sort of a dashboard which shows you how the performance is, like just a much better version of a task manager for your code. So that can be powerful in enabling, your operations. Okay, so I just gave you like a little taste of dask. And so here's an example of a much more complicated task graph. We saw a very simple one, but task graphs can be like this, or like, I made ones that are much more complicated than this. This is just good looking, so I'm showing it this over here. So this is like all tasks operating on data, and the red means it's waiting for some task to complete and so on. So it's, you see how it's like running in parallel. So that's what dask does. It takes your tasks, generates task graphs, like implicitly parallelize them. In many cases, it can be like very powerful at the get-go for me, these sort of operations. But I wouldn't say it's always best for everything. And so if you compare dask versus something more fundamental like NumPy, if you have a smaller problem size, you still want to use NumPy because there's an overhead of generating all these task graphs and this parallelization. So dask gets really powerful when, for example, you want to analyze terabytes of data, but you only have like a desktop computer with like 16 or 32 gigs of memory, right? So dask lazy loading is especially useful in such cases. So because it only loads as much memory as it requires for the present chunk, and the whole concept of chunking, it does it piecemeal, like the computations, instead of doing everything at one time and like crashing the memory. Okay, so I have to start wrapping up here because it's time. So some of the key takeaways, the things I want you to take away is, we talked about two very different things. The first one was the CESM post-processing tool. We saw how the pi averager, pi reshaper, components of it, they can be very powerful. They're very integrated into the whole post-processing workflow that we talked about. So they can also be used independently outside of that. But there are also downsides to the post-processing tool in that if you want some new diagnostic sets and those sort of things, it's like, yes, you can use the climatology files, but don't expect to be able to modify the diagnostic sets to give it exactly what you want. But then the Pangeo framework I mentioned, because it's it's up and coming, and it's a buzzword now, and in a couple of years it's going to be like even more mature. So, and I mentioned xarray being like a representation of netcdf. Then plotting using CartoPy, matplotlib. Then finally, dask works implicitly with xarray to enable like very quick parallelization. Of course, I got to show you very little, but I hope that taste was enough to like sort of get you to ask more questions about what can dask do for you. And as it is right now, don't expect the Pangeo framework to do everything NCL can do. It's still in development. There are a lot of people working on it, but it'll take a couple of years till it reaches that level of maturity. But if you're like starting, if you're like looking to learn sort of a new sort of a thing, instead of using something established, I would say consider using the Pangeo framework. Okay, I'll leave you with some additional resources. And finally, acknowledgements. I want to thank everybody at the HPRC team, Lisa Perez, Kristen Ting, Sanjeev, Depeng, Fred, and Alper at NCAR. So yeah, thank you. And now would be the time for questions, if you have any. Okay, in terms of like, I believe the question about swapping the axis is with the xarray plots. And yes, there are more advanced syntaxes that if you check the documentation, you should be able to swap the axis. And does dask work along with a for loop? So that depends on exactly what you want to do. It can work with a for loop. So the one thing I've mentioned right now is, so for example, we computed a mean, and the mean function was implicitly defined in xarray. But what if you wanted to define a function for yourself, and the algorithm wasn't like present in xarray? So of course you're going to have to like write your own function, right? And that is, so you still have to like abide by the rules of like lazy loading and so on. So you still want to use however xarray does it. You want to do it along the lines of that. But in terms of like enabling your own like a parallelization for your own function at dask, there are options with dask delayed, where you can simply like loop over some data set, and every time in the loop you can like submit a job that'll be computed whenever dask gets around to it. So it's not like compute this immediately. It's more add this to the stack, and then the dask scheduler will get to it when it has the available resources. And of course, that's a question. I'm learning it too, because it's sort of a new technology. But yeah. Any other questions? You can also raise your hand. Okay. Okay, so Jason asks, generating averages, editing the env_process.xml, env_diags.xml. Okay, so that's a good question. So let me go back. Where was this? Slide 32. Okay, thank you. Okay, I think it's here. Okay, so the env postprocess.xml, that's common to the entire package. So all the components. But just like you have env_diags_ocean.xml, you also have one for atmosphere, one for land, one for ice. And correspondingly, the ocean averages, like just like you have ocean averages, you have atmosphere averages, and you have ice averages and land averages, and also the diagnostics. So the reason why all these are like separate components is for many people, they're usually a domain expert. So they're not going to be needing like diagnostics for all the like a lot of people may not like care about the land diagnostics. So that's why it's like separated. But that said, once you have configured everything up properly, it shouldn't be too hard to like chain everything together. It shouldn't be like, I believe there is a script which can do that, but I haven't tried it out myself, so I can't speak to that. Cool. Any other questions? And I'd encourage to play around with the materials I've given to you in the course folder, and also like take a look at some of the notebooks. And if you need any further resources on xarray and everything, please let me know.